My name is Henry Harbison, and this is my Physics 2211 Lab 4. The main purpose of this lab is to use Newton's second law and the energy principle, and we're going to predict and model the motion of a mass in a spring system, and I used the video provided in the lab sample link, and then uploaded that video into Tracker and tracked the X and Y position of the object. From that, I made the CSV file with the values and uploaded that file into my Glow script code to compare the expected and the values I got from the fundamental forces. The fundamental forces used in the lab are Newton's second law and the energy principle. The second law states that an object will keep moving at a constant speed once it's in motion, assuming zero net force, which is a momentum principle, and we'll use also the energy principle, and the formulas in that include gravitational potential energy, spring potential energy, and kinetic energy as well. And then from that, we can use those formulas to aid us in our lab. The energy formula is the change in kinetic energy plus the change in potential energy, and in this case, it's equal to work, but work is zero, so it's not included, and these are the other formulas involved in it as well, all more equations that we need. We'll use the equation seen here for a period, the spring force equation, and then solving for K, which is just moving around the period equation, setting it equal to K. We can use this to find other unknowns. We can also expect that the results of the lab will show the experimental data. This should be pretty similar to the graphs we predict, and it should follow a similar path with only minor differences being caused by human error. We also assume that the only forces in the beginning acting on the mass are the spring and force of gravity, so we can set them equal to each other and solve for L, which is the original relaxed length. We can neglect air resistance as well. So here is solving for K, as we found earlier, and this is solving for L. First, you said Fg equals Fs, and then L, and we just plug in the values for it. For the initial conditions and systems and surroundings, the system is the mass springing and Earth. There is no surroundings. Initial position is seen here. Initial velocity is just zero. The gravity is 9.8 meters per second squared. We start at T equals Z, and then L and K are the same as before. The time per oscillation is 1.54 total seconds as found in the video, and mass is 0.402. And the original length is 7, which is also found in the video. In this experiment, we used option 1, and I uploaded the video into Tracker and was able to track the positions of the mass and then got the graphs of it in terms of X and Y coordinates. Here's a Glow script code. These are the initial conditions, and here are the constants for it. As you can see plugged into them, here is the calculation loop. This is a gravity-only simulation graph, which is X position versus time and Y position versus time. And as you can see, they're pretty similar to what we expected and what we got in our model. For the similarities and differences, from the graph, we can see that the expected value and experimental values are pretty much the same type of motion, peak and dip at the same time. They follow similar periods and intervals, but it's a little different as it varies, as it's a little off. Like you can see a little gaps between it, but the period is a little off, but it's still similar. Possible sources that could cause human error are because I had to go frame by frame and get the data. All forces such as air resistance and drag were neglected because we didn't take those into consideration, and the video could have also distorted it, which can make height look different. So the energy principle satisfied, so as you can see with the orange line, it shows that the energy has been at zero the entire time. This means that it remains unchanged, which means that the energy was not added or lost throughout the motion of the thing, or it wasn't added to the system. Thank you.